on Oemof.Solph. Today's subject is district heating optimization. Oemof.Solph is an open source energy modeling framework, and in this case I want to provide you with an example and I want to explain it. The three main topics today are optimizing the district heating, saving the results, loading the results, and of course analyzing the results. The goals today is learn how to save and call the results without running the simulation. So we can run big models and we can call the results in a separate script, and thus we can put all the analyzing tasks we have in a separate script, and we can decouple running the simulation and actually analyzing what the results are. We then want to learn how to model selling and buying electricity on the wholesale market via the electricity grid. We want to model the dispatch of a district heating grid, very simplified, but nonetheless it's a beginning, and we are going to analyze the results by creating some plots. The sources are shown here for the script as well as for the data. I will put all the links in the description of the video and you can check it for yourself. All the scripts I'm going to use you can find on GitHub. This is the energy system we are going to talk about today. It consists of two sources, a gas source as well as an electricity grid source. If we go to the top left corner, we start from the gas source, we go to the gas bus, we then go to the power plant for the gas. This power plant produces electricity and thermal energy. This thermal energy is then stored in a thermal storage system, and it then is used to fulfill the thermal demand, so the heating demand, for example, of a city. We then have the electricity grid on the top right corner. It's going to the electricity bus, which is then going to the power to heat converter, which in turn is feeding into the thermal bus, and the electricity bus is also feeding into the excess electricity sink, so we can sell the electricity produced by our power plant on the wholesale market. As you can see, we have two sources, three buses, two converters, one storage component, and two sinks. To get an idea of the dimensions of our system, we turn to some numbers. We have a heating demand of around 350,000 megawatt hours per year. This is approximately, depending on your consumers, but think about it as a city of medium size, let's say 100,000 people, with a maximal/peak demand of 150 megawatt per hour. We have CO2 emissions of natural gas of 0.201 ton CO2 per megawatt hour. We have to buy certificates for our CO2 emissions on the wholesale market. Our power plant has a capacity of 200 megawatt electrical power and 225 megawatt thermal power. We have a thermal storage of 900 megawatt hours, and we have a power to heat converter with a power capacity of 10 megawatt electrical power. This is an overview of the input data. It's real data from 2022, except for the thermal demand profile. This is not taken from 2022. We will look at each of the curves separately in the following graph. As you can see, in the year 2022, we had quite high gas prices here in Germany, reaching up to 300 euros due to the invasion of Ukraine. So it's in a sense a special year because of the major role of outside effects going into the prices on the wholesale market, but nonetheless it's the data we use in this example. This gas price is in turn influencing the electrical price, or the price for electricity on the day-ahead market. As you can see, it correlates quite significantly. This is because of the merit order system, where gas-fired power plants are very often setting the price. The CO2 price is between 70 and 90 euros, so it's quite stable. And this is referring to the European CO2 certificate market. And lastly, we have the thermal demand profile, which quite clearly shows that most of the demand is located in the winter, spring and autumn, when in the summer we have very low demand. If we look at the script, we first of all have to account for the feed-in revenues. So we have to add the sink and the prices of the electricity exchange. You can see the script on the left side. Because revenues are negative costs, we have to multiply them with -1. We don't have any consideration of taxes, etc. However, it would be quite easy to add them depending on your nation's regulation and so on. We then add the source for the natural gas, here with the label R gas for resource gas, which goes into the bus gas. And the variable cost is the gas price and the CO2 price, which we have read in from a data file. in the form of a CSV spreadsheet. We have to convert the gas price to kilowatt hours. That's why we divide it by 1,000. For the CO2 price, we have to account, first of all, for the conversion from per ton to per kilogram, so by the factor 1,000, and we also have to account for the CO2 intensity. Depending on your study, you will find different numbers. In this case, it's the number shown here. We then add this to our system. In the lower half of the script, you can see how the electricity grid is added, and in this case, it's a source, so we can buy electricity on the day-ahead market from the grid for the costs of the DAA day-ahead market price time series, and this is considered as variable costs here. Again, no consideration of grid fees, other fees, etc., but depending on the location of your system, your country, etc., you can add these quite easily. We now look at the first converter. It's the CHP plant, which converts gas to heat and electricity. In our case, we just added as a converter for now. We will improve on this model in a later video. For now, it's just a simple converter. We give it the labels PP power plant CHP, and we give it bgas as an input, and we give it electricity and thermal as output buses. And as you can see on the right side, I have assumed an efficiency of around 90%, with an electrical efficiency of 0.421 and a thermal efficiency of 0.474%. This is again from the top of my head, and it's a static number in our case, so no matter the load of the power plant, it will always have this efficiency, which is not very realistic. However, for the current setup, it's sufficient. This gives us a thermal power of 200 megawatt and an electrical power of 225 megawatt installed capacity. The second converter is the power to heat system, which is converting electricity to heat. We assign it the nominal value of 10E3 kilowatt, which is 10 megawatt of installed power to heat capacity, and the conversion factor is 0.99, so 99% of the electricity is converted to heat. The storage system is very important because it allows us to decouple the production of thermal energy and the consumption of thermal energy. Again, these numbers are just from the top of my head. I have assigned it a storage capacity of 900 megawatt hours with an input power and output power of 50 megawatt each. The outflow conversion is set to 99%, and we assume that there is no loss rate. If you want to save the results, you can use the following script. We first of all save the energy system results main and meta from the operational model. We then get the current working directory and assign a file name, and then we call the function energy system.dump to save the results at the location we desire. If you want to call the results, for example, in a separate script, we again get the current directory and the file name, and we then read the results file by creating an energy system and then restoring the results into the energy system we have created. These charts show the thermal flows. On the top, you can see B thermal to demand underscore thermal, which is the flow from the thermal bus to the thermal demand. In total, we have 350,000 megawatt hours, and it's shown here. In the middle, you can see the flow from the power plant to the thermal bus. It's 357,000 megawatt hours. It's a little bit more than the total production. In the middle, you can see the flow from the CHP power plant to the thermal bus, and at the bottom you can see the flow from the power to heat converter to the thermal bus. As you can see, the sum of the production of the CHP power plant and the power to heat converter is more than the total demand. This is due to losses in the storage component. In this graph, we can see the storage inflow with a total sum of 294,000 megawatt hours. You can clearly see the seasonal pattern. In this next graph, you can see the storage outflow with a little bit lower total sum of 287,000 megawatt hours. This is due to the losses within the storage system. So we put more energy in than we get out, since some of the energy is lost within the storage component. And in this graph, you can see the storage content, which is between 0 and 900 megawatt hours. And again, you can see the seasonal pattern because the storage is utilized much more frequently in the winter months compared to the summer months. This is the last graph. It shows the three previous graphs in one to simplify the comparison. You can again see the seasonal pattern as well as the difference between the sums of the flows. And This gives you a good impression how important the storage system actually is for the economic optimization and the economically most profitable way to produce the thermal demand and actually earn revenues on the wholesale market by selling the electricity produced as a byproduct. Thank you for watching this video, and please, if you have any questions, check out the scripts I will link on GitHub or post a question in the comments. Thank you.